Thank you, Davide. Thank you, the organizer, for the invitation. So indeed, today I will talk about nonlinear waves along this torus of fluid. So this work has been mainly done by Philip Nowkowski, which is my PhD student, and in collaboration with Shitwang Pham. But before talking about shallow water phenomenon, I would just like to show you the large facilities we use to study deep surface gravity waves. So we use the largest non-military basin in France, which is located in Nantes, with Félicien Bonnefoy, which is 50 meters long, 30 meters large. And we use this basin generally to study resonant wave interaction experiments or to show gravity wave turbulence experiments. We have recently also studied the statistic of thousands of rock waves generated in such isotropic wave field due to inverse cascade wave turbulence. And as told Stéphane Randou this morning, we use also a 1D wave flume, 150 meters long, to study 1D propagation of deep gravity waves. So we can see coherent structures coexisting with random waves. We also see the emergence of peregrine solitons within these random waves. And as told also Pierre, we can control their occurrence in space and time within the flume by IST. Okay, so let us return to the torus of liquid. So the main motivation is to wonder ourselves if a periodic, curved, and 1D system lead to significant difference compared to the classical straight geometry for wave propagation. But it's a difficult task to generate this structure because the torus tends to close its hole by capillarity in order to minimize the free surface. So how to create a stable torus of liquid? So we can use a superhydrophobic plates. So I will try to do the experiment at the end of the talk with the help of Nathan. So we use this kind of plates and we render it superhydrophobic. That is to say, the contact angle with the liquid and the plate is 160 or more degrees. So this prevents the torus to form a closing hole, and we also machine an axisymmetric weight-shaped groove running along its perimeter. And this groove prevents the torus from closing its hole because the fluids need to move on the slope. The slope is quite slight, it's typically 4 degrees, and we can, just by pour water, we can change the width of the torus from 1 centimeter to 3 centimeters typically. The typical radius is 7 centimeters. And so by putting a camera located at the top of the experiment, you can detect the outer boundary and the inner border of the torus. And you can also measure the azimuthal wave amplitude by a single probe at some location. So with this setup, you can study azimuthal waves along the inner and outer border of the torus, as you can see here. So now, if I apply the sweep sign forcing, that is to say, we force the system monochromatically, but we change slightly the frequency in time, so we can reach the experimental dispersion relation of the linear waves. So how to do that? We just take a space and time Fourier transform of the movie of the border displacement, and we end up with this figure. And you see that there is a rich spectral structure in form of several propagation branch, several modes, and this one corresponds to the usual gravity capillary branch. But not that you have this parameter which quantify the curvature of the radial curvature of the torus, and also you have an effective gravity since the fluid move along the slope. And typically you reduce by a factor 10 the Earth's gravity. You have this branch also, which corresponds to the center of mass of the cross section of the torus, with can move up and down like that. And the cutoff frequency here correspond typically, you can do that of a solid ball oscillating within the triangular shape. And then the other one here corresponds to sloshing waves, which is also a coupling with a transverse mode, but here that does not move the center of mass. So you have, since you have multiple modes, you can have multiple sloshing branch here. So it is a very rich structure that we will see at the end of the talk, that it is very important to have this, notably to have a free wave resonant interaction. So if now you force the system much stronger and with impulsion instead of monochromatic forcing, what you observe is two counter-propagating structure generated just by pulling the system. So are they soliton or not? So to answer to that question, we can use two different plates, a large plate and this one, a small plate, 4 centimeter in diameter or 7 centimeter in diameter. So first, how to generate a soliton? It's quite simple. You use a wave maker and you pull, and just by capillary effect, it stick the liquid, and then it generates these two counter-propagating waves. So if you take now the space-time Fourier spectrum of this pulse along the torus border, what you observe is that the energy is concentrated around a line of slope that corresponds to the pulse velocity. And you see that the velocity is lower than the velocity of gravity, linear gravity waves, meaning that this pulse is subsonic. So this dispersionless feature is a spectral signature of solitons. And we can also try to make collision between this head-on collision between two depression solitons along the torus. So you can see here an angle time plot, and in this domain here there is the interaction that it is enlarged here. So we mark only the minimum here by the dot, and you see that the collision evidences a long residence time that is proportional to the width of the torus and also to the amplitude of the solitons, inversely proportional to the square root of the amplitude of the soliton. And you see also that he experienced a slight phase shift after the collision. So these also are a feature of solitons. So how to model this? We can use the Korteweg-de Vries equation, but for a torus it's slightly different. So here you have the usual dispersive term, here you have the nonlinear term, and you see that there is this parameter about that quantifies the curvature, and also this factor here, which depends on the form of the shape, the bottom shape. So as you know, you have Sech solution of this equation. So we check this with our pulse that we have measured, which is the cross. There is a very good agreement with no fitting parameter. And also you can follow this profile along the torus. And as said Nicolas for his experiments, you see that when you plot on a rescale variable, it keeps a self-similar profile during its propagation, even if you have a slight dissipation. You can check also the soliton width, which is predicted by KDV, and say that the width is inversely proportional to the amplitude of the solitons, and it works also very well with no fitting parameter. And note also that depending on the value of the bond number, which quantifies the capillary effect over the gravity one, you see that if this is positive, you need that the amplitude should be positive, and if this is negative, the amplitude should be negative. So it controls the elevation or depression profile. So you can also measure by time of flight measurement the velocity, and you put on the rescale variable. And so you compare with the prediction of the KDV, which state that the velocity of the soliton is linear with its amplitude. And so indeed, this is what we observe experimentally. And so it is well described also by the KDV prediction. So it's at this, so I can discuss also this. The bond number select the soliton profile, as I explained previously, in the straight geometry, and in the torus, this is roughly the same. Typically, there is just this curvature K here that appears, and also for the critical bond number, instead of being 1/3 for the straight geometry, this is 1/6. And if you insert this value here, you can predict the torus size at which the profile has to change. And indeed, we find experimentally that the elevation soliton and with respect to the depression one change when the radius of the torus is like that. So it's quite in good agreement also. So all the experiment that I show you previously is well described by KDV prediction with the large plate. So now if you take a smaller plate, this one, for instance, 4 centimeters in diameter, I will try to show you that the periodicity effect will be very important. So indeed, if you make the same as previously, you pull to generate solitons, you compare with KDV solution, etc. You measure the wave velocity. What you observe, quite surprisingly, is that you populate this quadrant of this velocity versus amplitude plot. So we observe subsonic, because this is below the linear velocity, subsonic elevation solitons, which is not predicted in the straight geometry. And I will show you that it is due to the periodicity of this toroidal system. So indeed, if you consider more general solution of the KDV equation as cnoidal wave solution, it involves an elliptic parameter m, which is when equal to 0, you have a cosine, and when it is equal to 1, you have a sech, and in between you have nonlinear periodic wave. And since you have a periodic domain, you need to wrap the solution on the circle, even for the cosine. And then this imposes a boundary condition on the KDV equation. So if we do that with our experiment, so you have just the 2π periodic condition is just this one, where n eta is the number of solitons, delta is the width of the soliton, and this is just the period of the cnoidal function, where k is elliptic integral of the first kind. So this periodic condition leads to this condition, which link the amplitude with this elliptic parameter. Both parameters are not free; they are completely linked. And if you plot the amplitude of the soliton as a function of this elliptic parameter for 3 different torus widths, this is these 3 solid line here. It separates a region between subsonic and supersonic for a critical m star value that I will show you why in the next slide. And experimentally, we have a maximal amplitude compared to the width of the solid. Typically, we cannot increase more than 20% of the width. So we cannot observe things above this. So this means that this region will be very hard to see, and we will see only subsonic one. Okay. Another thing that we can do is a phase diagram between the parameter W, the width of the soliton, and R, the radius of the soliton, or the radius of the plate. So you see that with the large plate, you can plot this 2 solid line coming from this just by separating domain from quasi-sèche solution to conoidal solution, just to close to 1, 0.999. And so you have this region here. And experimentally, what you see is that with the large plates, we can reach only the quasi-sèche solution, which is the if the torus is very bigger, this is close to the straight geometry. And for the small plates, you see that you can range the conoidal solution, but also the sèche one. Okay, so if you use the prediction of KdV for the velocity of conoidal solution, you have this term here, and you need, as I tell you previously, you need to add the periodic boundary condition linking m to the amplitude a. And if you do that, you can find this dashed line here that correspond for different widths of the torus. So it is reasonably in good agreement with our data, and it means also that the velocity is now nonlinear with the amplitude of the wave, contrarily to the usual case for m equal 1. And so it means also that the periodicity authorizes the presence of this subsonic elevation solitons. And also, if you by equalizing this quantity to 0, you can find the crossover between the supersonic and subsonic soliton, which is close to this value here. So to sum up, there is new type of soliton that occurs due to the periodicity. I show you this for the subsonic. It could be also this one for supersonic cases, but we cannot reach them because of the Rayleigh plateau instability that breaks the torus in small droplets. Okay, so we have also implemented periodic inverse scattering transform in this system, and we have experimentally validated in this geometry. Indeed, if you take the signal at this value, you have 2 depression solitons here. And if you do that, you find eigenvalues indeed that correspond to 2 solitons and radiative pulses here. For the rest of my talk, I would like to show you other nonlinear phenomenon using this geometry. So we are now far from the domain of validity of KdV because we use a very different forcing. So we can use a sinusoidal forcing, as you can see here, and we can wonder ourselves if we can transfer energy by nonlinear resonant interaction. And if you have a large number of random nonlinear waves that interact with each other, generally you can reach a wave turbulence regime. So this is the question that we can discuss here. So first, we force the torus at a monochromatic frequency, as you can see here. And then you can also turn the button to increase the forcing amplitude. And so what you observe if you do a time frequency spectrum is that you have only the mother wave here. And by an interaction, you have the 2 daughter waves that appears when the forcing is strong enough. And if it is further strong, you find a lot of waves that are generated by interaction. So this generation is called a triadic resonant instability for internal wave, or parametric subharmonic instability if F2 equal F3. And we have to check also that it is verified also for wave number. So indeed, resonant wave interaction are like that. So wave need to verify this and also this, both being related by the dispersion relation. And you can for 1D, you can easily solve this problem graphically. And you see that for gravity capillary mode, far from the gravity capillary transition, you have only convex gravity capillary branch, and you cannot find wave point that satisfy this. But if you add branches, new branches, the sloshing branches, the green one, for instance, here, you see here that you can build free wave that satisfies this, this resonant wave interaction. So the interaction between the two propagation modes authorize three-wave resonant interaction. So we can check this experimentally. So here you have the frequency, here you have the K, and you force the system close to the here this is the reminiscence of the sloshing branch, and here the reminiscence of the gravity capillary branch. So if you force the system close to the sloshing branch, you switch on, you light up this point, also this point from the gravity capillary branch, and you also light up these 2 points that verify the relation in wave number and in frequency, but with using the sloshing branch here and the gravity capillary. It does not depend on the forcing if you are close to if you force near the sloshing branch. If you force near the sloshing branch, you find the two daughter wave, F2 and F3, and if you do the sum of this, you find indeed that is scale with F1. So you have a three-wave, two branches interaction involving in this system. You can also check if you are at twist forcing how the daughter wave increase with time. So the growth rate. So the yellow is the mother wave, and the two other color is the daughter wave. So after a transient, once the mother wave has reached a stationary state regime, you see that the two daughter wave increase exponentially as expected for an instability. And also an important point is that if you plot the sum of the total phase of the waves, if they respect the resonance condition interaction, this is 0, and you end up only with the arbitrary constant here. So you expect that the sum of the total phase is a constant. And experimentally, it is what you have once the transient is far, and you have typically total phase with its constant pi/2 here. And so this means that the three waves are phase locked, and they can transfer energy during this phase locking. Okay, and so now, if you force strongly the system, and you put the spectrum here, so you force here, you see that you have a discrete set of peaks here, and if you enlarge near the forcing peak, you see that you have the mother wave here, the daughter wave generated by the triadic resonant instability, but you have also these daughter waves that will interact with each other. For instance, that leads to the yellow point here, or with the mother wave that leads to this point here. And these granddaughters will interact also to generate granddaughter and so on. So you populate the spectrum. So it's this is a work in progress, but it is a very good trial to observe wave turbulence because we demonstrate that we have resonant interaction in this system. And then if you, instead of forcing monochromatically here, you force with a narrow band forcing, I think we will have a straight line here, characteristic of wave turbulence. So it's time to conclude if I want to do the experiment, because as you know, experiment does not work at the first time. So maybe we'll need 2 times or 3. To conclude, I show you that we succeed in creating a stable torus of liquid, and then to study the azimuthal wave propagating along the torus. I show you that the linear wave have a complex spectral dispersion relation, leading to several propagating modes. And the periodicity of the system leads to new solitons, such as subsonic elevation solitons, and this their velocity depends non-linearly on the amplitude. So one open problem in this system is what I heard in this room is it will be possible to make a soliton gas in this specified geometry. We can try to think about this. And if we are far from KdV hypothesis, I show you that you can have three-wave resonant interaction in this system, and a cascade of three-wave resonant that can be generate maybe a route to wave turbulence. So I would like to thank the Simon Foundation and also the French government from the funding. Thank you very much.
Thank you, Eric. So let's try to produce the experiment now, or?
Yes.
Yes. Let's see.
So maybe I have to just show you something. Maybe Nathan, can I?
So let's wait for question. Maybe let's give Eric some time just to set the experiment, and then hopefully when the experiment runs at the first tentative, we can maybe then ask question to Eric during the experiment runs.
Okay, so this plate is super hydrophobic plate. That means that we are so. Nathan, can you switch off the light, because this means that it is covered by a spray, a commercial spray, typically loosely that leads to some pillars at nanometric scales, and it is very well known in nature since you have this in the lotus leaf. So you see that you have typically a spherical drop here. So the angle of contact is 160 or 70 or more, and so you can you can see well, but this is a guy. We have some liquid without never wet, and with never wet. It's just gliding on your. I'm not working in never wet. Okay, so we can try this. So you see, this is the plate which is machine to have the. I don't know. I think you don't see here. To have the small groove. So the important point is to have a very good horizontality. So I will try to make just one drop to see you the super hydrophobic effect first. So you see that there is loosely almost no dissipation, because the content line is. So if I don't, you see where, yeah, okay. So I can try now to do the torus. I guess the horizontality is not so good. So experimentalist, the best way is the subway ticket. Paris ticket, yeah.
You mentioned them as well.
Yeah. We're close. And the horizontality is not good. Okay.
Almost there.
So the torus is, I don't know if you see well. Ah. So the torus is larger here than here, meaning that this is a very good level, by the way, if you want to. So you can generate waves. So I have only a pen. So and to do a soliton, it's more tricky. So that's it. So it works.
Thank you. Right. Question for Eric. Mark.
Very nice. Thank you for the demonstration. It's fun. Can you operate near a zero dispersion point in your KDV model? It looks like you have this crossover between elevation and depression waves when those two coefficients cancel. Do you see a change in the structure of the wave patterns when you're very close to that resonant point? Higher order dispersion, basically.
I tried this effect on just on the straight case. So changing the bond number from the depression solution to the elevation solution and to be as close as possible to 1/3. But experimentally, either you have the depression solitons or not. I never managed to I see what you think about, to have the fifth order term to see. I didn't manage to observe something at this, but it's maybe one time I tried. Maybe with this one.
Any other question for Eric? Yes.
So maybe I missed it. How do you change the bond number?
Sorry?
How do you change the bond number?
The bond number, so you can maybe Nathan, maybe peut-être you can do that. Okay. You can change the width to show you the.
So it's click the screen and then it'll move.
So you can change so this is, the bond number is this. So W tilde is just half of the width. So you can change the width just by pulling more or less water, or you can change also the total radius of the system. So this is what I mean here. For large bond numbers, a lot of capillary effect, you need to have this for the radius. And for a small bond number, you have to be large system.
Thank you.
Any other question for Rick? Well, if not, let's thank Eric again and all the speakers of today's session. And also Nathan for helping in setting up the experiment with the cameras.
And I would like to thank Nathan with his help for the construction of the experiment.
So maybe we can leave the experiment for a couple of minutes if someone wants to go and play.
So please don't touch the surface. You can touch the water, but don't touch the surface, because otherwise the small pillar that you have seen disappears. So we need to rebuild. It's not complicated, but
thank you. Very nice.
Thank you.
Je me demandais,
je
me demandais si vous voulez faire une photo de tous les speakers de ce matin.
Ah oui, bah, ça, faut demander à l'organisateur. Oui. Nicolas, tiens. Je viens de
Au moins ceux qui ont parlé maintenant.
Ah oui, on peut faire une photo, oui, si vous voulez.
Pensez aussi.
Devant Newton?
Ouais, ouais, à la limite.
On va faire une photo devant Newton.
Pour enlever la tâche là.
Like for the plate and all that. How much would it cost?
At the plate, it's just you need that someone at your lab make the machine.
Okay, so
So it costs nothing if you okay. And there is only the never wet that the spray is very cheap. It's commercial, so I don't know, $20.
Okay.
On va faire une photo devant Newton.
Attends, s'il dit des bêtises là, tout le monde.
Okay. One extra. Thank you very much.